Hello and welcome to the lecture on Félix Candela and the hyperbolic paraboloid. Today we're filming in the Engineering School Library at Princeton University, where behind me you see some of the models that students made back in 2008 about the structures of Félix Candela. These models traveled to several art museums to illustrate the idea that structural engineering, can be a form of art. In today's lecture, we're going to look in depth at Félix Candela, not only his works, but also his personality and some life experiences that shaped him. This is actually one of my favorite lectures to give, so I hope you'll enjoy it. We're going to begin by defining the hyperbolic paraboloid form. This form is also referred to as the hypar, and we're going to examine why did Candela favor this form. We're going to look at some of Candela's significant structures, such as the cosmic rays pavilion, the many umbrella forms he designed, Milagrosa, which is a church, Los Manantiales, another church called Cuernavaca, and finally the Bacardi rum factory. We're going to look at the differences between what is a master builder and what is a structural artist. They're similar, but there's a subtle difference between these two terms. We will also explain Candela's process from conception of form, to the calculations, to the constructions he made, and finally we end with an examination of his evolution and his designs, from imitation to innovation, and finally inspiration. Let's begin by looking at Candela the person and some life experiences that shaped him. He was born in 1910 in Madrid, and he was an excellent student as well as an excellent athlete. By the age of 15, he was a strong athlete in many sports, including skiing, pole vaulting, rugby, and diving. And just like he excelled in these sports, he excelled in academics. And by the time he graduated, what would be the equivalent of high school, he wasn't sure what vocation to follow. And a somewhat whimsical decision, he decided to try his hand at architecture. He applied to the School of Architecture, and he was admitted into the school in Madrid in 1929. During this time that he was a student of architecture in Madrid, he developed an interest in thin shell concrete structures, but this was not part of his formal education. He learned about these through the publications that were coming out mostly through France and Germany. At that time that he was a student and had this interest in thin shells, another famous engineer called Eduardo Torroja in Spain was designing thin shell structures. In particular, he was at the time building fronton recoletos in Madrid. Candela found out about it and knew Torroja would be on site, so he went on site to see Torroja. Fronton recoletos is a singly curved barrel shell that was actually destroyed during the Civil War in Spain. When Candela went on site to visit Torroja, he writes this of his experience. He says, quote, "I found Torroja on top of the formwork and asked him to explain in general terms how the enormous barrel vault would function. He did not answer me very affably, which hurt my feelings. Later, he gave a conference at which he described with a grand array of equations the calculations he had made, but like most of the audience, I could understand practically nothing." So it's interesting that he went to see someone that he admired, but the person he admired wasn't very kind to him, and he found the calculations very difficult, but he wasn't dismayed, and he persevered and went on, we know now, to become one of the greatest thin shell designers ever. From what Candela could gather from his frequent and what he referred to as assiduous library visits, quote, "The general opinion in the technical literature was that the key to the construction of the shells was in the domain of advanced mathematics." That's Candela's quote. So he went to the library and he pulled out papers that were written in German by the Germans, and he took a German-Spanish dictionary, translated the German to Spanish. He learned the advanced mathematics, and he copied by hand what he would see in these journal papers because he didn't have the money to purchase them on his own. Later on, many years later, when he did have that money, he would purchase it, and you see on your screen his handwritten notes besides what he was studying, and this is a paper by Finsterwalder, who was one of the great shell builders from Germany. His ambition to become a shell builder, a shell designer, continued through his education, and finally he got a break. he won a scholarship to travel to Germany and study beside Dischinger and Finsterwalder, who were two of the great Germans publishing these papers on thin shell structures. Here's an image of Candela and his colleagues and friends as they wish him farewell. He's about to go to Germany and achieve his dream. Candela arrives at the train station in Spain, about to board the train to Germany, and at that very moment, civil war breaks out in Spain. So Candela never gets on that train and instead stays back and fights in that war. He fights on the Republic side, and he's eventually sent to a concentration camp. So he never achieved his dream of studying with Dischinger and Finsterwalder. But he says that he does not regret the path that his life took. He felt that the lessons of the Revolution and the Civil War were more useful to him than the lessons he could have received in Germany. In 1939, at the war's end, Candela was exiled to Mexico, where only 2 decades before a revolution was raging. And it was in Mexico that Candela would grow to become one of the world's greatest designers of thin shell concrete structures. Before I continue describing to you Candela's shells, I want to give you a sense for how thin they were. Candela's shell structures were 4 centimeters thick, 1.5 inches in translation. So what does that mean in terms of scale? Let's think of it in terms of an egg. So we're all familiar with eggs. Eggs are 0.4 millimeters thick, or 1/64 of an inch. And this egg was designed by nature so that you could take it and squeeze it with your hand. As long as you apply uniform pressure on this egg, you won't be able to break it. All right? You could try this at home and you'll see how strong this egg is, even though we know how thin it is. To give you a sense for the scale for Candela's structures, we look at what's called the span to thickness ratio of these structures. So for an egg, it's about 60 millimeters high, 0.4 millimeters thick, so 60 divided by 0.4 gives you a span to thickness ratio of about 150. The larger that number is, the thinner your structure is. So if you look at one of Candela's thin shell structures, for example, the Bacardi rum factory that I'll come to at the end of the lecture, we have a span of 31 meters, a thickness of 40 millimeters. That gives us a span to thickness ratio of 775. So we could think of Candela's shells as about 5 times thinner than an egg. So that gives you a sense for how thin these structures are. Let's examine Félix Candela from our 3-part perspective: the scientific, social, and symbolic. From the scientific perspective, we see geometric forms, the hyperbolic paraboloid, abbreviated HYPAR. From the social point of view, he arrives in Mexico after the Mexican Revolution, about 20 years later, and this is a time of political and economic stability. So this was a good time for Candela to arrive and start building and designing. And from the symbolic point of view, he's designing in concrete. This is a material that now represents post-revolutionary Mexico. It's inexpensive, it's forward-looking, it's efficient. It's something that breaks from the past Mexico, the Mexico previous to the revolution, to the Mexico after the revolution. When Candela arrived, it would be 10 years before he would start building his shells and come back to this dream of designing shell structures. He had studied the shell structure design from the mathematics and the papers of the Germans and the French, but now he wanted to start building some, doing some experiments. So his first experiment was of a funicular form. A funicular form means that if you were to take this shell and hang it upside down, it would be in pure tension, so that if you flip it, now this form is in pure compression. And through this experiment, he learned a lot about the practical aspects of designing thin shell structures. He learned, for example, that the minimum practical thickness was 4 centimeters. Candela's shells, as I mentioned, were mostly of the hyperbolic paraboloid form, and this is where he would become famous by using this geometric form. So now let me describe this geometric form of the hypar. The hypar can have curved edges or it can have straight edges, but the main point is it's a surface with curvature in 2 directions that's generated with straight lines. So you could think of it as a saddle on top of a horse, or a Pringles potato chip. If you're from the United States, you know about Pringles. So it's this shape which has curvature in two directions. The red arrow and the white arrow represent curvature in two directions. But you can see by the straight line generators that you can generate this curvature using straight lines. So this idea of a straight line generator and of the hypar provided some advantages for Candela. And these advantages are why he favored the hypar. So from the scientific point of view, the hypar has double curvature. Double curvature in a shell gives greater stiffness than single curvature. An example of a single curvature shell would be, for example, a barrel form. From the social point of view, the straight line forms, we have greater economy of construction because now he can use straight pieces of wood as opposed to curved pieces of wood to form his design. And from the symbolic point of view, we see infinite forms that are possible from the hypar, and this leads to the elegance and the creativity of his designs. Let's start with examining his first hyperbolic paraboloid shell, the Cosmic Rays Laboratory, completed in 1951. Only a year earlier, Candela had begun his construction company called Cubiertas Ala. So for this project of cosmic rays, he was hired as the building contractor. The initial design for this project chosen by the architect Jorge González Reina was a barrel shell. But Candela took over the design and made a few changes. For example, he redesigned the supports to make it this arch shape to match the shell. He also added corrugated screens to enclose the space, the front and back, this white screens that you see that are corrugated. And the reason that he corrugated it is because he said he, quote, liked the play of the shadows. Most importantly, Candela changed the form to a double curvature, from a barrel to a hypar, reasoning that the extreme thinness of the shell would require the added stiffness found through this hypar shape. The director of the construction at the University of Mexico, where this Cosmic Rays Pavilion still stands today, he asked Candela to make the roof no thicker than 5/8 of an inch because it had to be thin enough to emit cosmic rays. Now Candela knew, again, to give it this rigidity, he had to give it double curvature. So again, the rationale for moving from a barrel to a hypar. If we dissect the Cosmic Rays Pavilion, we see a few parts to it. For example, there's the platform and the stiffening arches. Then you have the hypar shell that sits on top of that, and the corrugated concrete screens that enclose the space. These screens are not structural. They're there just to enclose the space. They do not hold up the shell. When we look at the construction of the hyperbolic paraboloid shape of this cosmic rays, you see the straight line pieces of wood that form or generate the hypar shape. On the inside, we can see these arches that are intended to stiffen the shell against buckling. In hindsight, we know that those arches weren't necessary because the hypar makes a natural stiffener with the uplift of the shell, and therefore analyses have shown that the shell is stiff enough against buckling without those arches.